So let's track the motion of this object. We pull it down here at t equals 0 and we let go of it, true? When it comes back to this position, it's going to be a full period, is it not? So when it gets up to the middle position, it's going to keep going. It's going to go to some position that's 3 feet higher. And this is going to take a half a period. And then it's going to take another half period to come by. So how long does it take to get back to the middle position? So Emmy, how long? It takes half a period to get all the way to the top. So let's do it with our pendulum. The period of motion is the time from here back to here, agreed? So how long does it take just to get to the center? A fourth, agreed? Takes a fourth.
So 3/4 to get.
3/4 to get back to the center, and then 4/4 back to original position. So it takes 1/4 of a period. But how are you going to find out what the period is? Well, you know from our circular motion that omega equals 2 pi over t. We've already determined that omega equals 2. We know that omega is equal to 2. So that means that t is equal to pi. So you solve this equation for t. So t is equal to pi. Therefore, t over 2 is equal to pi over 4 seconds, the first equilibrium, t over 4. Okay. So if you notice at the top of 888, after 394 words, he also arrives at t equals pi over 4. So I'm not sure words are the way to go. So that concludes the first one, number 1. Now, is the object heading upwards or downwards when it first comes back to equilibrium? Is it going up or down?
Sorry, when it first comes.
When it first comes to this point after we let go of it, is it headed up or down?
Up.
Set it up. Okay. So we've answered those 3 questions. Now, part 2. If an object is attached to the spring and released 3 feet below the equilibrium with an upward velocity of 8 feet per second, find the equation of motion of the object. What is the longest distance the object travels above the equilibrium position? When does this first happen? Confirm your result using a graphical utility. No, we won't confirm it using a graphical utility.
Didn't tell us that.
Good. Now, the only thing that changes now is that when this object is pulled down, then it is kicked upwards with a speed of how much? 8. So what they did with this object was just what we're doing with this pendulum. They pulled it to its x0 position, and then they kicked it in the direction of motion, which means that it goes further in the other direction. So now, which has a higher amplitude? When I just pull it and let go of it, or when I pull it and kick it? When you kick it. So you see the amplitude changes because it has this V0. But remember what I told you about pendulums and all simple harmonic motion. The frequency is independent of the amplitude. The frequency is determined by the mass of the spring. So if you kick it, have you changed the mass of the spring? No, so the frequency doesn't change. So we don't have to redo the frequency, we already did it. If the frequency doesn't change, does the period change? No. All grandfather clocks have a period of 1 second. So it doesn't matter how big the amplitude is, the period of all pendulums is determined only by the system, not by the amplitude. So in part 2, the only thing that changes is A, the amplitude. You have to calculate a new A. That means that this number changes and nothing else changes. That number changes and nothing else changes. So let's see what the new number is. Now, x0 is still 3. V0 is now 8. Omega hasn't changed, it continues to be 2. So what is 8 divided by 2?
4,
What's 4 squared?
16.
16. And what is 2 squared? 3 squared is 9, agreed?
Yes.
And what's 9 plus 16?
25.
And square root of 25?
5.
5. So the new part of the problem, the 3 is replaced by a 5. Okay? Now, after 472 words with arc signs and pi's over 2 all over the place, he also gets a 5. So we've finished now our presentation to you of all of simple harmonic motion, which is a fairly complex topic. And I wanted to be sure to give it to you on a Thursday so that you would have 5 days to wrestle with it. And in particular, Saturday afternoon, I would hope, to wrestle with it, or appointments with Lynn or myself. And this is really an application. What we just did was physics. This is Physics 101. And that's what we're going to be doing for all of Chapter 11. You're going to be doing some surveying. How wide is this river? You're going to be doing some navigation. How do I get from New York to Long Island? So it's now applications of trigonometry. That's what we're going to be doing. And this is our first and perhaps the most complicated of simple harmonic motion. It's really a physics topic. If you take a physics course, you'll see exactly the same thing again. So we dabbled, and it was good. Okay, now I'm bringing that to a conclusion. To my knowledge, we will not revisit simple harmonic motion again in the course. It's a standalone item. So you won't be seeing it again, I predict. If you have any questions or comments, we can make them now. If you want to go upstairs immediately and thank Ted Loya for my demonstration equipment budget. He was worried that Maryland couldn't afford it. And then we will go to putting your stuff on the whiteboards. So anything that we should do before we do that? So let's get started.
You mean demonstrating the problem?
Pardon me?
Are you?
We'll put your assignment A7 on the whiteboards, page 874. What you wanted to do when you first walked in. That was that. So we're on page 874. And people have said that these were slow going, so we're going to find out. First, let's do 3 problems each. Are we ready? 3, 6, 9, 12, 15, 18, 21, 24, and 27. Now I did 24 on the front board, so that should be fairly straightforward. Okay, let's throw those up there and take a look. And I'll rearrange the camera so we can catch your masterpieces. So please do tell Kayla that this video